Hi everybody, I'm the greatest living inventor, and today we are doing my invention of quickened time. Let me write it down. Quickened time. Okay, it's the second time that I'm trying to record this. It's really long, it's 13 pages almost, and I need to rush through it. Okay, so all the links will be in the description of the video, and forgive me for not explaining everything. I invented a new explanation for how cosmology works that doesn't require dark matter and dark energy, but it does require us to think differently about time. Okay, standard explanation. Okay, this is the wrong explanation. This is what the scientists today think. Standard explanation. Wrong. Universe expanding faster. All the stars and galaxies appear to be moving away from us. The further they are, the faster they are moving away. So scientists think there is a mysterious energy in the vacuum of space itself that acts in the opposite way to gravitation. Gravitation pulls objects closer together, but this mysterious energy pushes objects farther apart. Because they don't know what it is, they call it dark energy. Okay, so forgive me for not writing everything. I'll just write it in points. Universe expanding faster. So they call it dark energy. Okay, galaxy rotation curves. I'll first explain. The way galaxies are turning around is different from our solar system. In our solar system, the more distance a planet is from the center, it takes more time for it to rotate around the center of the solar system. For example, Mars encircles the Sun in about twice the time of us. On the other hand, in each galaxy, matter go around the center of the galaxy at the same time, whether it's closer to the center or closer to the perimeter. So the whole galaxy rotates as a single block. So scientists think there is invisible matter near the perimeter of the galaxies that binds it all together like glue. So to rotate as one piece. So scientists think there is invisible matter near the perimeter of the galaxies that binds it all together like glue to rotate as one piece. They call this invisible matter dark matter. Okay, so galaxy rotation curves. They call it dark matter. Gravitational lensing. Okay, this is the next point, gravitational lensing. Intuitively, we feel that light travels in a straight line, but Einstein's relativity tells us that gravity pulls on light like on us. So when the light passes close to something heavy, it bends a little towards it. This causes the gravitational lens effect. We can see what's behind the heavy object like a cluster, because the light of what is behind it bends around the object like light does inside a lens. The heavier the object, the more lensing it causes. But clusters make more lensing than what they should have, according to the mass of their visible matter. So scientists think there is more matter in the clusters which we cannot see. Again, they call it dark matter. Okay, so this is another proof, so-called, for dark matter, gravitational lensing. Okay. Okay, now this was the standard explanation, the wrong explanation that scientists believe. Now for the alternative explanation, my explanation, the right explanation. Okay. Alternative explanation. Okay, this is the right explanation. Okay, so now this is the invention. Time can speed up. From Einstein's relativity, we know that time isn't constant everywhere. According to this theory, time is passing at our time's normal speed always, except in these two situations. Time slows down the more we get closer and closer to a black hole, great mass, and time slows down the more we travel faster and faster closer to the speed of light, great acceleration. My theory, on the other hand, is that time can also speed up. I think time is, okay, speed up. I think time is like the number line, and the 0 point, the origin, is on the rim of each black hole, the event horizon. I think the further we get away from such black holes, the faster time flows. Scientists believe that at the center of each galaxy, including our own Milky Way, there is a black hole. So I believe that between the galaxies, deep in empty space, time runs very fast. I also think that inside black holes, time flows in reverse. Time runs backwards, like in a movie that you rewind backwards. But we will not talk about this now. So, what does this mean? What does my theory dictate? the further we get away from a black hole, the further we get away from a black hole, the faster things are happening. What is happening in the rim of a galaxy? Spinning. So the rim, the perimeter of every galaxy actually does spin faster, fast enough to compensate for Kepler's second law that slows it down. So these two opposing effects balance each other, and in every galaxy all its parts spin in a uniform rate. So this explains the galaxy rotation curves. No need for dark matter. Now let's think about what we see. Okay, so I made you a picture. I hope it will focus. Okay, you can freeze it now that it's focused, and this is the picture I'm talking about. On the left there is our eyes or a telescope. On the right there is the object that we are seeing, and on each step there is a TV screen, and then a VCR like video cassettes, and then a camera like a closed circuit TV camera, CCTV, and so on and so on and so on. Okay, so this is our mental picture. Now let's think about what we see. Let's say that we are looking at some object, but not directly. Instead, we are looking at a TV screen that is connected to a CCTV camera. We watch the object in real time. Ignore the small delay. Now let's put between the screen and the camera a video cassette recorder. In parentheses, VCR. Yes, I grew up in the 80s. Close parentheses. That records from the camera and after that plays to the screen. If the VCR cannot play in fast forward, then it's just like before. Ignore the small delay. But if the VCR rolls the recording of what the camera captured in fast forward speed, then we see it on the screen. The object looks faster than in real time. Now, let's say that the outer space between our eyes and the faraway object, for example a distant quasar, acts in much the same way as a long chain of screens, video recorders and cameras. Okay, so we have eyes. Remember the picture. You can roll back and freeze. Pause. Eyes, screen, VCR, camera, and so on and so on. Screen, VCR, camera, star, object. Here I try to draw on the left side our eye and on the right side the object, for example a quasar. In the middle of a chain of cameras, in the middle a chain of cameras photographing screens that display cameras that photograph screens and so on. In parentheses, and between each screen and camera there is a fast forwarding VCR, close parentheses. The playing speed of the VCR is dictated by the speed of time where the VCR is. In deep space between the galaxies, time is very fast, so the VCR plays very fast forward. You also understand that the longer this chain is, ignore the small delay, the faster our eyes will eventually see the object moving or doing what it does. Because of the accumulated fast forward of all the VCRs between us and the object. Okay, this one does it, this one does it, this one, each one accumulates between us and the object. This explains why faraway objects look like they are moving away from us faster and faster the farther away they are. So we explained the universe expanding faster, no need for dark energy. Okay, now lensing. Let's understand first how optical lensing works. I have a Swiss Army knife that's called that's called Swiss champ, and it's got a magnifying glass. When you touch the glass with your fingers, you feel that the magnifying glass is fatter in the center and gets thinner when you are closer to its perimeter. So the light passes slower through the center. Okay, we're on page 3 and minute 15. Okay, we need to hurry. A similar thing happens in gravitational lensing. The light that passes through the center of the cluster passes near black hole or black holes, where time is slower, so that light moves slower through the cluster. This gives us the extra lensing effect. So again, there is no need for dark matter. Okay, now time as a vector field. Okay, so this is like another on top of this invention. So far this was the invention, and now we are talking about another layer above this invention that relies on the previous part. So now we are talking about time as a vector field. Okay, so this is something else, and it requires, you will see, but it's like another invention. Time as a vector field. So far, without explicitly saying it, I treated time like a scalar field, where in every point in space there is a number which tells us what's the speed of time there, like in temperature. Okay, this is called scalar. If the number is positive, time moves forward. If the bigger the number, the faster the time there. If the number is negative, time flows backwards. Again, the bigger in its absolute value the number, the faster time runs backwards. Of course, if the number is 0, time stands still in that point. And it's like you pressed freeze in your VCR. What if time is not like the field of temperature, but instead it's like the field of electricity and magnetism? This is called a vector field, because in every point in space we have not just a number, but an arrow of certain size pointing at certain direction. The vector field of the magnetic field can be seen using small iron rods, functioning like plotting compasses. Video thanks to Uniserve Science Video. Okay, so the video is called the PHEMF demo something, and I'll show you what it looks like. Okay, this is the upper video here. Okay, so you see tiny arrows, which are compasses inside the glass. Okay, so the vector field of the magnetic field can be seen using iron filing, here floating in mineral oil. Video thanks to Uniserve Science Video. So again, this is another video from the same people. I'll put the links in the description, but I hope you can, the camera will focus and you can see I'll give you the link in the description and you can see the video by yourself. and there it's moving and it's cool. Okay, so if time is so affected by gravity, then maybe they are both two sides of the same coin. Okay, time and gravity. Is the relationship between them similar to the relationship between electricity and magnetism? A movement of the one produces the other and vice versa. Moving an electrical charge, current of electrons flow inside the wire, creates magnetic field. Moving magnet creates electric current, moving electrons in a wire. Let's check. Where do we have moving time? Okay, so now we are talking about gravity and time. Let's check. Where do we have moving time? Black holes have a large effect on time, so we will refer to them as time charges, like electrical charges. When two black holes rotate around each other, they create gravitational waves. The LIGO experiment found them. Maybe it's more accurate to see the gravitational waves as equivalent to the radio waves, oscillating fields of electromagnetism that build each other. So maybe gravitational waves are gravity fields building a time field, building a gravity field, building a time field, and so on and so on. What about the opposite? Do moving gravity charges, masses, create time? In my theory, this is the solution to the final parsec problem. So in my theory, this is the solution to the final parsec problem. When two galaxies collide, their black holes, in the heart of each galaxy there is a black hole, merge. At first the black holes miss, pass by each other, and then again, but closer, and so on. When they are at a distance of 1 parsec, a few light years from each other, there isn't enough material between them to get them together. So theoretically this should take billions of years, longer than the universe's age. But we do see binary black holes that merged. So there is a problem. What happens in the last parsec? How do they come together so fast? My solution is that it doesn't happen fast, but instead it does take billions of years, but they generate time, a lot of time there that encapsulate itself. Okay, so because there are moving charges of mass, there is a creation of time. Whatever is in there is running fast forward for us. In fact, I think the similarities run a lot deeper. Okay, so it takes a lot of time, but because it's running fast forward for us, because there is this creation of time, then for us, from the outside, it looks like it happened fast. Okay, so it's like inside there is a lot of time, outside it takes it's slowly and normal time, but outside to us it looks like it happened fast. Okay, Now, in fact, I think the similarities run a lot deeper. Cosmic inflation explained. In a simple bar magnet, it has a north pole on one side, which is the source of the field, and the south pole on the other side, which is the sink of the field. The lines of force go in arcs from the source to the sink. I claim that the same way time also has a sink, which is a black hole, and the source, which is a white hole or Big Bang, or a Big Bang. I think also this explains what happened in the Big Bang of our universe, how it happened so fast, and especially the cosmological inflation or cosmic inflation. Scientists say at the inflation stage things happened very fast. The universe inflated almost at once. This is easy to explain if you see the Big Bang as a huge source of time, so creating time. And within this huge amount of time, the universe could have enough time to inflate. And only from outside, this time looks like it happened very quickly. Imagine a gradient of time flowing from this singularity, where all the time in the immediate vicinity of this point runs extremely fast, and the further away you go, the slower the time gets, until you get the more normal time speed, which is where we are, for example. Okay, so we got an explanation to cosmic inflation. Now, next point, origin of the universe. Origin of the universe. I'll drink something. Okay. Sorry. Origin of the universe. How can we find this location where the Big Bang happened? I thought of two strategies. Both lead to the same conclusion. Go towards where the time is faster. Strategy 1. Move up the gradient field to where the time field is strong, which means time runs faster there. In this way, we will reach either a local maximum, a white hole, or the white hole of white holes, which is the real maximum, the Big Bang place. This would be similar to someone walking with a compass until he reaches the North Pole. But in this metaphor, we have scattered about strong local magnets. For example, MAGLAB in Florida. One way to rule out this divergence is to look what generates this time field when we get to the center. Okay, look inside. Another better way to avoid these local ones is to spread the search in different directions and compare for the most universal source. Consider that it's possible that the time field dispersed, in parentheses, like the cosmic radiation, which is coming now from all directions equally, close parentheses. Okay. Strategy 2. Move the root, move to the root of the orrery, okay, orrery, O-R-R-E-R-Y, where absolute movement is 0, which means time runs faster there. As you know, the Earth is rotating around the Sun, and the Sun is rotating around the center of our Milky Way, and our galaxy rotates around the local group cluster, and so on. This orrery, okay, orrery is the mechanical device that simulates planets. So this is like an orrery. This orrery series of gears or cogwheels isn't infinite. At the end of it is the center of the universe, which is logical to assume is also the location of the Big Bang. How do we find it? Since our absolute speed is a composite of the movement of the Earth's movement and the Sun's movement and the Milky Way movement, then we are the fastest. Since the faster you fly on spaceship Earth, the slower time runs according to relativity, then our time is the slowest. To get to the roots of the tree that we are on, we need to go to where the time is faster. Okay, so we got to the same conclusion. Okay, now another title. Exiting to 4D, the fourth spatial dimension. Okay. If we do find the location of the ultimate white hole, then this is the place where we can enter the fourth spatial dimensions. In parentheses, if you count 3 spatial dimensions and fourth is the time, then call it the fifth spatial dimension. The fifth dimension. I call it fourth because I talk about 3 dimensions, and this is the fourth spatial dimension. But if you talk about time as fourth dimension, then you're talking about fifth 5D. Okay. How do we do this? Let's get back to the magnets metaphor. The following wonderful pictures are from the Flickr account of the gifted Dinah Mason. Okay, Flickr. Okay, so I'll show them to you. It's much easier than to paint. In this demonstration, the compasses are on a plane. Their needles show the field. Okay, so showing this to you. This is the first picture. Okay, this is a magnet and compasses. Here the compasses crowd the whole plane 2D. Okay, the whole 2D plane. So this is another picture where there are compasses all around. In analogy to the compasses limited to their 2D plane, we are limited to a 3D space. The things that control our space are gravity and time. So how does this help us to find higher dimensions? We use another property of the analogy, which is that two same-time poles repel each other. Here, ring-shaped magnets are threaded on a rod. Okay, stick. The rod doesn't support them. It's just there so that they don't flip over. So I'm showing you, okay, the upper picture. Here you see how strongly they repel each other. They are floating in the air. Okay, this is the lower picture. Okay, they are floating. What do we need to do to get to the next dimension? We need to somehow be lifted off from the glass plane. Okay, we are the compasses, or in the area of the compasses, and we want to get to the higher plane, higher dimension. Imagine we have two bar magnets on the plane, and one of them is very heavy, so it's not mobile. Let's suppose it's glued to the table. Let's also say that the other magnet is free to move freely in that plane. Let's make it a air hockey table with no friction. Then we slide the mobile magnet, give it a strong push, so it glides towards the immobile magnet. If all this is too much for you, just think of a tiny magnet thrown towards a huge magnet. Now, what will happen? If the moving magnet is free to rotate, it will rotate so it is attracted to the fixed magnet and they will stick to each other. Okay? So this is the upper picture. So this is the upper picture. So it rotated and they stick to each other now. But if we can make sure that the moving magnet is aimed with same type of pole towards each other, prevent it from flipping over, the moving magnet will most likely be knocked off the table. Okay, so this is the lower picture. Okay, they are with the same type of, it doesn't focus, but you see enough to see that they are in the same, the middle has the same kind of polarity, gray to gray. Don't know why it doesn't focus, but okay, this is the most that I can do. Okay. Why is the moving magnet thrown up from the table? Because we cannot aim it precisely to be head-on in front of the other magnet. So the immobile magnet throws the mobile magnet backwards at random. Since the original plane is only one of many possible planes that exist in 3D, then it's most probable that the original plane will not be selected and we will fall off the table. How do we apply this to our situation with the sources and sinks of time and gravity? I think the analog here is to drag a white hole and shoot it fast towards a bigger white hole. This task is unfortunately not in our powers to do yet, but what we can do is look for places where this already happened in the past. And search for the breach of the fourth dimension by looking for places where radiation is lost into emptiness, in parentheses, where the radiation escapes to the fourth dimension, close parentheses. Sorry. By the way, the idea that gravity leaks into the fourth dimension is not new at all. This is one explanation of why gravity is so weak compared to the other forces. I think it's safe to assume that in the location of the Big Bang there was the equivalent of white holes slamming against each other. So there has to be an opening there. Again, if this portal is still open and we can use it, in parentheses, now without the violence of its creation, close parentheses, to enter the fourth dimension. Okay, so if this portal is still open, then we can use it now without the violence of its creation to enter the fourth dimension. Okay, now entering back to 3D, our normal reality. Okay, entering back to 3D, our normal, so-called our normal reality. Assuming that we can enter the fourth dimension safely, which is not trivial at all, in parentheses, see the second answer to this question in stack exchange physics, close parentheses, there is a question, how will gravity behave in a fourth spatial dimensions? And they talk about how much the density of things is different and so on. Okay, how do we find our way back to the table? In this demonstration, the iron filings are on a transparent glass plane. I hope it focuses. Okay, I'll bring it closer slowly. Okay, you can freeze when you like what you are seeing. Okay, so now you can see the magnet with the iron filings on the table. Okay, you can freeze. In this demonstration, the iron filings are on transparent glass plane. They align along the field lines, but mostly limited to the same 2D plane by gravity. 44 minutes, okay. Okay, so I'm showing you the next picture. Okay, I'll try to do the same trick. Come closer slowly. Okay, can you see something? Okay, you can freeze now. theoretically, all the arcs, curved field lines exit the North Pole and enter the South Pole. But the only one that is special is the straight one that goes along the bar magnet. This is the shortest one. So in our time-gravity analogy, what will we see? I think we will see thin threads of realities that go in different speeds. Okay, some longer, some shorter. One is the shortest. The reality line between the time source and the time sink is closest to the gravity, so that reality will run in the slowest pace. Okay, so this is the reality that we want to come back to. Okay, now last thing. Okay, William James Sidis. When you Google smartest person ever, you find the sad story of William James Sidis. According to Wikipedia, Sidis was amazing. For example, in his book in 1920, he predicted the existence of dark matter. Okay, in 1920, 100 years ago, a little more. But he also predicted that time can flow in a different way in different places in space, what we would now call outside of our galaxy. Okay, this is amazing. I'm quoting to you. We say, therefore, assume that in the part of space and time under our observation, which we know is very limited, the preponderance is towards the positive tendency. So again, we may therefore assume that in the part of space and time under our observation, which we know is very limited, the preponderance is towards the positive tendency. We may suppose that there are other parts of space and other periods of time when the preponderance will be in the reverse direction. Okay, we may suppose that there are other parts of space and other periods of time when the preponderance will be in the reverse direction. Okay, this is amazing. It's like, I think it's 100 years ago. I only read this after I thought about this myself. Okay, that different places can have faster time. This is essentially what he is saying. So I see it as a case of great minds think alike. Okay, thank you very much to these gifted artists from Icon Archive for their beautiful icons. Okay, so from Icon Archive, Janik Baumgartner, star on icon, Iron Devil, video cassettes icon plus telescope icon plus tool icon, BEOS, B magnify icon, Ether Brain, Live Cam 1 icon, and Icon Factory, Old TV icon. Okay, so that's it. So this is my inventions, or couple of inventions, and I hope it was clear, and thank you very much. I'll see you in my next invention. Thank you very much. Goodbye.